Hello everyone. So today we have James Beattie giving the CITA seminar. James is a joint research associate at Princeton and a CITA fellow, and he'll be talking about magnetohydrodynamic turbulence today. So just take it away.
Hi everyone. I'm James, as I think I know most of you. So thanks so much for letting me present here at CITA. Feels like it's been a while, CITA seminar incoming. And today I'm going to talk about one particular thing. I kind of had the choice to do lots of little things or one particular thing in some detail. And I decided to go for one particular thing in some detail. That thing is going to be supersonic magnetohydrodynamic turbulence at extreme Reynolds numbers. So the subtitle here too, turbulence is less turbulent than we think. We're going to have to dive into some nice theory about plasma relaxation as well. So it's going to be a bit of a pedagogical talk, and that's how I like to give all my talks. But we'll also do some interesting kind of turbulence research on the frontier as well. So first, I just want to situate ourselves in the universe. Of course, we all know the universe is full of different scales. We have the largest scale of the dark matter web. And we zoom into the junctions between the dark matter filaments, and of course we find galaxies on order KPC. And we zoom in even further into these beautiful disk galaxies that I have here on display, and we find the interstellar medium. And this is, of course, where all the surf students like to think. So interstellar medium, let's talk about it a little bit. It is a plasma. It is a multi-phase transfer supersonic compressible plasma. It has really large Reynolds numbers. So we'll talk about Reynolds numbers in a sec. But essentially that means that the nonlinearity in the momentum equation is much larger than the viscosity in the momentum equation. That describes the plasma. And this makes it very, very turbulent. Now the turbulence itself can be driven by a whole different zoo of sources. So these can be gravitational instabilities in the disk of the galaxy, supernova explosions, stellar feedback, etc., etc. These are all different mechanisms for injecting momentum and energy into the plasma. And of course, it's pervaded by relativistic particles with non-negligible energy itself. Densities peaked in the GeV to TeV range. So these are the cosmic rays that we all love to think about if we think about ionization, if we think about chemistry in the medium. And very non-Gaussian in general. So the whole medium is essentially a log normal, has kind of log normal density structures. And these log normal density structures are very much related to the star formation. These describe the filaments, the ribbons, the striations, the sheets that we see in the interstellar medium. Also, dynamically important, maintain magnetic fields. So that is that the magnetic Reynolds number, and we'll also talk about this in a little bit, is very large. So it means that the induction in the induction equation is strong compared to the resistivity, which means, again, highly chaotic turbulent magnetic fields permeating through the plasma. I like to kind of think about it as there are these four horsemen of the ISM physics. And I mean, you can kind of interchange these horsemen with different things depending on how interested you are. But these are my horsemen, at least. The compressible turbulence, the turbulent magnetic field, the GeV, TeV cosmic rays, and the feedback. And you can see them kind of, jumping on the ISM astronomers, plasma physicists, and high energy physicists. So all of these very hot topics, you can search this in NASA ads. If you're into ISM, these are probably kind of the four pillars that you're really interested in. But today I'm just going to be talking about these two fundamental horsemen, the compressible turbulence and the turbulent magnetic fields. Norm, what do you think? Horsemen? You got some other horsemen in mind?
No,
there's a good horseman? All right, that's good. So let's start simple. Let's talk about momentum conservation in a hydrodynamic fluid element. Of course, the momentum equation just looks like this. You have your thermal pressure. You have your viscous stress, you have your nonlinearity, which is the source of the turbulence, and this is just the momentum evolution. So as I said, you have your Reynolds stress, your viscous stress, or you can just say the quadratic nonlinearity, and an operator on your plasma that essentially smooths out the nonlinear things. So when you take the ratio of the thing that's producing nonlinear things and the things that's smoothing out nonlinear things, you get the plasma Reynolds number. And you can see that already, I mean, when you have a very large Reynolds number, then you're just going to create a lot of nonlinearity in your plasma. And if you have a very low Reynolds number, you're going to be dominated by the thing that smooths out all the nonlinearity. So this is really what the Reynolds number is capturing in a way. So now I want to talk about what happens in a plasma as you go to very high Reynolds numbers. So, like we said, this is the term that's going to dominate. So this is going to be important for us. I'm just going to consider two sine waves. You can barely see this one. This one is blue here, but there's going to be two sine waves. And they're going to be interacting. They're going to be interacting through the nonlinear term. Now, what does this look like? Well, I just take my two sine waves, I put it through the nonlinearity, and you can see that I produce essentially another sine wave, just with a little bit of trigonometry. And as long as I'm doing things like momentum conservation, where I can sum up my k modes from each of the sine waves, essentially the k mode of this sine wave is just going to be the sum of the two sine waves. What does that look like? Well, it means that I have grabbed these two waves here, this blue one that you can't see, this red one here, and create a higher frequency wave. Very, very simple. I'm just adding little sine waves through the nonlinearity. I keep doing it, play the same games, keep pressing play on my nonlinear term, and I get more and more sine waves. Now, the creation of these new high frequency terms, you can kind of already think in your mind, I've got these high frequencies interacting with each other, and they kind of cascade into smaller and smaller scales, right? I'm creating higher and higher frequency waves, smaller and smaller waves. And it all happens on this nonlinear time scale associated with the Reynolds stress. So there's some kind of nonlinear time scale for the interaction between these waves, and we're creating more and more smaller waves as we wind the crank, so to speak. And if you do this ad infinitum, what you end up is with a full cascade, where essentially, you have your low K modes here. So now we're in spectral space, so we're just plotting the K mode of the sine waves and the energy in the sine waves. And we're just plotting them, and you can just wind that on, you're going down this cascade until you get to small Reynolds numbers, where the Reynolds number is approximately 1, and you essentially get back into the linear regime. So this is kind of this is where the cascade comes from. It comes from that nonlinear term. As you saw from my Blackboard talk, it really is the Reynolds number, the Reynolds number, the size of the nonlinearity on the outer scale here, that is going to set the size of this cascade. So if the Reynolds number is quite small, then maybe there's only a few interactions before the viscosity matters. So you get a small cascade. But when the Reynolds number is really, really large, you get a larger and larger cascade, and therefore the Reynolds number sets the size scale of the cascade, or the total energy. Now, there's a bit more that I want to say about the cascade. There's kind of three things here. That the waves are essentially, there's a constant energy flux between the different K modes here. This is one of the assumptions from Kolmogorov turbulence. We think about local interaction, so we think about neighboring K modes interacting with each other. This K mode interacts with this K mode, etc., etc. You get this local interactions down the cascade, and also that things are incompressible. So all of these ideas, these are all eddies interacting, as Reed asked me about during the Blackboard talk. These are eddies, these are incompressible. They interact, they form this cascade. So that's what I want to say about the cascade. Let's go to a full galaxy now. Now you can kind of do some back of the hand.
So let me just interject real quick.
Yep.
Right? So you're saying it's incompressible.
Yep.
And on the ISM, often the Mach number, at least, is much bigger than that.
We'll get that on.
Okay. So you can just warn people.
I'm warming people up with the cascade, the Kolmogorov picture.
So, quick question. It doesn't come really intuitive to me. Why does the energy goes down when you have these cascades?
So, as in instead of the energy just being constant.
No, because you start with a higher energy and then you go this.
And then you give that energy to the modes below you, and you keep passing it down. So if this wasn't being replenished, because I have some replenishing source, I am playing God here, I'm injecting energy up here onto the low K modes, and they're passing that energy all the way down through some kind of self-similar interaction. If I stopped, this whole thing decays, right? So this is a really good point. This is the spectrum for a stationary process where the energy in here is equal to the energy out here.
I see that they pass out to like more modes.
They pass it out to smaller and smaller modes.
Remember when he did his trigonometric functions? He had a sine and a cosine, or a cosine and a cosine. He took the sum of the two. There's also a term which is the difference of the two. That would go to higher wavelengths.
Okay.
And there are cascades that go that way.
I see.
This is more to do with the turnover time getting shorter and shorter. That's why the energy is slower.
Well,
Well, what you're referring to is the energy flux is
Your
constant.
question is
the
about
energy
why-
flux is constant. The energy
Yeah,
flux
the
between
is
scales is constant.
But your question is why is it going down but not going up?
Hmm.
Well,
It's
it's not
because of
going down.
turnover time.
Oh, but they can also go up as well.
No,
Depending
but-
on-
Well, I mean, when you talk about up versus down, you mean the direction of the energy flux, right?
No, that's what sorry, the question is about energy flux direction or is it about this slope?
It's
Mm.
about this.
So in terms of slope, that's a different answer, it's because the turnover.
I'm not too sure if I understand the the turnover time is a function of scale here. It's fastest down here, slowest up there.
Exactly,
Why is that related to the?
because it stays
Because
shorter time.
it's V squared.
Yeah. Okay. Anyway, let's go to a full galaxy here, and here I'm listing out some Reynolds numbers. Exactly as I talked about the ratio between these two momentum equation components of the warm interstellar medium, the warm ionized medium, the warm neutral medium, and the cold neutral medium. Now these look like between kind of 10 to the 7 and 10 to the 10. And the mean free path, by the way, is very small for the ISM. So really these are nice collisional plasma. So we can approximate the ISM very well with MHD fluid, which is very nice because it's not true for all the other I ... ends. So we know that the quadratic nonlinear term is very large on large scales in the galaxy. So it means we're going to essentially start creating kind of K-modes on smaller and smaller scales, exactly as we were doing in our kind of toy model interacting with sine waves. And we keep going down. And people have made measurements. This is just measurements of dust continuum from Herschel of the LMC here. And they're kind of beautiful dust map. They kind of segmented it into different regions, and then they've taken just the power spectrum of each one of those regions, and they get this beautiful self-similar structure. You can see I'm just zooming in on one particular region. So at least on the 1 kpc scale, I would say, I mean, this isn't a measurement of the velocity, like we were talking about velocities moving down small scale. This is obviously dust, so it's a bit different. There'll be some transformation between the two, but still you get this beautiful self-similar structure in the 1 kpc regions. So I would kind of argue that this is a power spectrum when you're riding the cascade. You're deep in the cascade, right? You don't see any turnover, maybe a little bit of turnover, but there's not much on larger scale. So the driving scale, the thing that's sourcing the turbulence is on larger regions than this, in other words. But I think this is a really nice little measurement. So?
And that's projected.
That's projected, of course, yeah. Which is always a problem as well. Deeper and deeper into the cascade. Now you can get down to, we're talking about PC scales now, and you start seeing things like Larson's law. I mean, Larson's law is just, at least the way that theoreticians think about it, is essentially just tracing the turbulence. The turbulence cascade for these clouds, so this is going to be kind of cold gas on these kind of scales. It's probably supersonic, which follows a different kind of power law than Kolmogorov. It kind of looks like this, L to the 1/2. And again, just tracing the turbulence. But we keep going down, right? We keep going down. As we go down, the Reynolds number is shrinking because the Reynolds number is, of course, a function of scale. So the nonlinearity is becoming more and more suppressed. That's right. I had this plot, this slide. So this is kind of the plasma conditions on this scale now. So we're down by essentially the cold gas, and this is kind of molecular hydrogen organized into molecular clouds. Of course, very low volume filling factor in selenium, 1 to 2% of the total volume. Cold, 10K, which means, of course, the sound speed is low. And then essentially you just compute the thermal line broad and compare it to the sound speed, and you get around Mach 10. So this is all kind of supersonic on these scales. Exactly as Norm was saying. A really, really huge density contrast. So, if you're thinking about modeling molecular clouds, you better be thinking about modeling very compressible turbulence with large Mach numbers, and very weakly bounded, I would say, not realized by their own self-gravity. And maybe this is up for debate, but these things really are like blobs of turbulent gas, kind of quite transient in nature, and threaded by dynamically important magnetic field as well. So that is the kind of structures on these scales in the cascade. Okay, so we keep going, all the way down to Reynolds number 1. And if you do some kind of back of the envelope calculations here, you can work out that if your outer scale of the turbulence is 1 kpc in the galaxy, then your inner scale, the scale in which the Reynolds number is 1, is about 1000 AU. So I just find this an amazing process in which you can transport energy across scales in the universe. Absolutely amazing. But why should astrophysicists care? Well, if you're a star formation theorist, which I know there are people in this room, you should definitely care. I know Christoph has done some very nice experiments, and my colleague Dong-Hee Nam, on essentially changing the cascade to go from k to the minus 2 to k to the minus 1 and measuring the initial mass function for stars. So this is, you have essentially a box, you have your turbulence, you change the cascade, you have gravity as well that collapses the box into stars. And then you do this many, many times, and you essentially grab all the masses of all those stars from those sync particles, you put them in a distribution function as a function of the mass, and you essentially find that the different cascades give you different types of high mass slopes for the IMF. Really cool. So the whole idea here is that turbulence support creates more energy on small scales. If you go to the k to the minus 1, of course, much shallower, you have more energy on small scales, and implies less high mass star formation. Now, at an even more fundamental level, at the level of just forming stars in this cold gas in the galaxy, essentially there are ideas around this is the gas PDF of a particular molecule, of just a toy molecular cloud, in this case, just a gas PDF. And you have all this underdensity stuff. So this is all low density, this is high density over here. And there's some critical density is the idea behind these models, which will start forming stars with some efficiency. Not all of it will form stars, but there'll be some efficiency, some fudge factor where this high density gas will form stars. Now the turbulence sets the width of this PDF. The RMS turbulence sets the width of this PDF. And not only that, but it's the cascade itself in these models that sets this S-crit. So essentially, if you want to talk about the star formation rate per freefall, so you want to make a prediction of how the star formation rate of a blob of gas, you want to grab its gas density PDF in 3D as well, so you can't do this with the projected. And then you want to integrate from here all the way up with some kind of proportionality factors to get effective star formation rate per freefall. So this is at least an idea. It's an interesting idea. But the idea is that this is also the gas PDF is set by the RMS turbulence, and the S-crit is set by the cascade. If you have your cosmic ray hat on, which I think some people do every now and then, and there are kind of these two schools of thought in cosmic ray physics about how cosmic rays are transported through the interstellar medium. There's a self-confinement camp, and there's this intrinsic turbulence camp. Now, regardless of which camp you're in here, the turbulence itself is the thing that's providing extra source of scattering of cosmic rays on large scales. This should actually be switched around. This is because this, but extrinsic turbulence, so your actual turbulent magnetic fields are providing the scattering on large scales, and for self-confinement, it determines the properties of the turbulent diffusion of the cosmic rays. So regardless of what kind of cosmic ray physics you want to do, you can't ignore the turbulence. I think that's all I wanted to say. Now I get to Norm's point. But what about shocks? Of course, we know the interstellar medium is a highly compressible plasma. Here's the beautiful W3, W4, W5 MC complex. And you see it's just been blown apart by either a strong wind or a supernova. Well, back in 2021, we attacked this problem by doing a very, very large hydrodynamical simulation. This was the simulation on the cover of Nature, the long and short of turbulence. I think they were talking about the length scales that we resolved, but it wasn't exactly clear. And we got this beautiful cascade where essentially you could show on the large scales, which were dominated by supersonic motions, you get Berger's type turbulence. So this is the v to the power of L to the 1/2 that I was talking about before with the Larson's law. And then on smaller scales, when you cross the scale in which the motions transition from being shock dominated to subsonic kind of incompressible mode dominated, you get into a Kolmogorov turbulence regime. So this was really neat. That's my Kolmogorov turbulence, that's my shock dominated regime. This is really neat. It says that the subsonic cascade is actually embedded in supersonic turbulence. It didn't have to be like this at all. And the previous ideas were really that the shocks will just essentially go on all scales and there'll still be a single power law, but it'll just be changed slightly by the nature of the shocks. But that is not actually happening here. it seems like there are two separate cascades. And I like to say compressible turbulence is asymptotically becomes incompressible at small scales. This is not actually obvious at all.
It is not. So why aren't they shocks at all scales?
What? No. Well, you take a discontinuity and you put it into Fourier space, and it goes to all scales. But that's not what's happening here, because there's a shock width, the particular width of the shock. So that width of the shock maps to this sonic scale that I was talking about. So this kind of maps to the sonic scale, and then you get into an eddy-dominated regime.
Can I ask, sorry, a disembodied voice from a distance. If you inject the bump in the power spectrum, how does it distribute itself, and does it form shocks as it's trying to get back to the Kolmogorov spectrum?
Well, it depends on a few things. It depends on what scale you inject the bump, and it depends on how much
Well, I
energy.
mean in the inertial range.
Well, now it also depends on whether the bump has more energy than the thermal energy or has less energy than thermal energy.
I'm thinking of more energy.
Well, then it should shock.
Yes.
It should go quickly down the Berger's cascade. And then, I mean, it should just look like regular Kolmogorov turbulence.
You mean after a while? So the Berger's is
Yeah,
actually,
but very quickly, very, very quickly, because shocks live only a very short amount of time.
yeah, so the Berger's regime is trying to get you down to the attractor, which is the Kolmogorov regime.
Well, I don't think you have to think about it like that. I think that the Berger's cascade is steep, it's fast. Shocks
Yeah.
live a short amount of lifetime, they have a short lifetime, and the eddies have a much longer lifetime.
Yeah, exactly. Well,
It's not that it's an
I think that's
attractor.
what I was actually saying, but anyway, go ahead.
I wouldn't call it an attractor though.
Well, it is. 'Cause if you
Well,
start
ultimately,
with energy,
Kolmogorov is the attractor.
Well, I mean, you could say the Berger's cascade is an
It
attractor.
is. It is also. It's absolutely.
Mm,
That's
Yeah,
what
but
you're
it's
telling us.
but
If
it's
you
a
say
fast.
pump,
It's basically a fast mode. Kolmogorov is slower.
Yeah, no, that's true. That's all true. Yeah, I wouldn't say it's an attractor yet, at least. I don't know.
have you tried experiments where if you put in supernova, for example, some scale smaller than your outer driving scale,
Yeah,
then they probably will disappear fairly quickly. Right?
Yeah, that's exactly what I was thinking of.
well, in the case of supernova, it's very different because there's components that are inverse cascade and there are components that are direct cascade. And but yeah, I mean, you do get this picture come back out of the supernova-driven turbulence as well. So I think, yeah, I know, I see what you mean. I see what you mean.
Can you say what you mean by intermittency?
Yes. So intermittency. I mean, it's a whole.
So the answer is no.
No. Kolmogorov turbulence is really a theory of Gaussian fluctuations, and we know that fully developed turbulence, at least at the Reynolds numbers we've probed as humans, has non-Gaussian components. And these come about, they can be like vortex tubes, they can in MHD they're current sheets normally, or they can be incredibly non-Gaussian components of the magnetic field. And they essentially, because they're non-Gaussian, they live everywhere in K-space. They dump energy everywhere, non-locally in K-space, and they shift the whole spectrum. So these are the corrections that we're talking about. These beautiful, the interesting models from Xi and Levesque, you essentially add a little tiny fudge factor based on the dimensionality of the dissipated structure, the dimensionality of the intermittent structure in your turbulence, and you correct for that. So that's what I mean by intermittency. Okay. But I mean, another glaring issue with that calculation is that there were no magnetic fields. And we know magnetic fields exist everywhere we probed in the universe, magnetic fields exist. I really love this image of the Whirlpool galaxy, just showing this beautiful, and this is a small scale magnetic field, I would say. Lots of like strong turbulent components to this magnetic field. Really beautiful. And of course, we're thinking about kind of cloud scale physics here. We're talking about supersonic turbulence. we zoom into the clouds, and I mean, they look magnetized as well. And you can kind of get from dynamo theory that the straighter the magnetic fields are, the stronger they are as well. So, I mean, the molecular clouds have very kind of strong, straight fields penetrating through them. And there are some beautiful models for molecular clouds actually being driven by converging flows along the magnetic field. But anyway, my point is that our simulation of this interstellar medium turbulence better have magnetic fields in it. Now, when we talk about magnetic fields, we can't escape that we have to write down the induction equation. And of course, we can play the same games we did before. The induction equation has a nonlinear part where V depends upon V, and also has a part that smooths out nonlinear things. So we parameterize that by the nonlinear, or by the dimensionless number Rm, the magnetic Reynolds number. Now you can essentially plot an RE, Rm, so Re is our plasma Reynolds number, Rm is our magnetic Reynolds number landscape, which I think is really neat. So you have Re on this, you have Rm over here, you have Re over here, and you can kind of work out where the state-of-the-art simulations have probed, at least back in 2019, where Francois made this plot. And that's about it, 10 to the 4 on each plasma Reynolds numbers, but you can see that everything kind of lives, at these extreme Reynolds numbers. Galaxy, I put the hot ionized medium, WIM, warm neutral medium, cold neutral medium up here. So we can't currently capture the RMs, the REs, in numerical experiments. So what I wanted to do during the last year of my PhD was create the simplest supersonic MHD turbulence simulation above RE 10 to the 6. That was my goal. So as a PI on this project, running a magnetized ISM simulation at 10,000 cubed. So this gives you REs of larger than 10 to the 6. And really I was interested in what the scaling of the energy cascade is in compressible energy turbulence with a magnetic field. You can see kind of a visualization of one of the 5,000 cube boxes here with the gas density shown down here and the beautiful tangled magnetic field, turbulent magnetic field in gray. What do I want to say? Well, I guess this currently still is the largest simulation of its type. 10,000 cubed, it took around 80 million core hours to run this simulation. So that's about, about 4,000 years if you ran it on your Mac, I think. So I guess that would be back in when we're just starting to kind of do farming as a civilization. So if you had this calculation back when we just started agricultural revolution, it would just be finishing now.
Could I ask a quick question again from a disembodied spirit? Can you tell me how those magnetic field lines in that beautiful how they're actually made? So it's a sub-selection of the data, and you've got this beautiful joining, but presumably from a voxelized or pixelized set of data. So how do you get such beautiful lines?
Oh, as in you integrate through the magnetic field to draw a streamline, and then you map a polygon onto it, and then you smooth the polygon afterwards.
Is
that what you mean?
Yeah, exactly. Just how they do it.
Yeah. So this is the model. This model has only numerical diffusion operators. So that is, we don't have an explicit operator for the viscous diffusion. We rely on the underlying grid for our diffusion, and the same for the resistivity for the induction equations. But we're very lucky in that we had an undergraduate student working with us to actually really characterize these operators very, very well. And so we can actually go from our ILES, this is called an implicit large eddy simulation, where these things are just set by the grid, to a Reynolds number. And we get Reynolds numbers around 1 to 3 times 10 to the 6 for this simulation.
Would it be possible to do the brute force thing where you put in some by hand, or is it too expensive? You just put in an explicit.
No, we can definitely do that. But I mean, the point is to maximize the cascade as much as possible.
No, I understand, but I just want to, that would be a check on whether you believe these back there.
Oh, we've already done that. Not on these scales, but up to 2,000.
Up to 2,000.
Yeah, that's actually how we characterize these operators properly. Yeah. And so that's where the simulation lives right now, up here, 10 to the 6. So definitely around 2 orders of magnitude higher in RM and RE. I mean, we're still not quite at that in stellar medium REs and RMs, but certainly solar wind, neutron star mergers. I mean, the RE is not much more than this.
Can I ask you to go back to the prior one for a second?
This one?
Can you show me how you're actually doing the stochastic forcing? Is
Yeah,
it
so that's
the
coming
source-
up.
Say that again? Are you going
That's coming up.
Okay, great.
And this is actually very nice. I'm just making sure I'm not running out of time, and I definitely am. People in the recent, and this is only recently, in the last couple of years, I would say, have really discovered some deep connections between reconnection happening on small scale in the MSG plasmas and the RM of the plasma. And this is really only this paper right here, 2022, by Shunfei. Essentially, once you go above RM 10 to the 5, then the small scales look the same no matter what. So if you go into this asymptotic regime up here, nothing's going to change as you go to higher and higher RM, in other words. That's the idea, at least. It hasn't been completely checked out numerically, but it kind of seems like it's worked. And that is because you get these current sheets. So these are current sheets forming on small scales. These are things that Bart Roberta loves to talk about all the time. And essentially what happens is the current sheets become unstable to the plasmoid instability. And this is what you're seeing in 3D here. So you're seeing current sheets like this, and you normally see them like this, and you see the current sheet here with the plasmoid instability forming. Now you're seeing it in full 3D where you have these big flux ropes of magnetic field going through the current sheets. And this makes sure that all the small scales are just essentially being destroyed by these plasmoid instabilities. So you go to higher and higher RM and nothing happens. It's just all kind of plasmoid. But this is a brand new idea in turbulence and it hasn't been completely accepted yet, but this is something we can test with this simulation, which is very exciting. Yeah, so as I was going to say, as soon as you get into this plasmoid dominated regime, you actually get a deviation from your regular turbulent slopes to a negative 11/5 for these particular types of plasmoids. So you should just see this forever at higher RM if this theory is correct. Now, the magic behind these simulations really is in this stochastic forcing, as Dick was just asking about. So let's talk about that a little bit. So the stochastic forcing term is essentially the solution to a OU process. And this OU process has two different components, really. So it has the second term here, and if you just kind of get rid of this term, you can just see that this is just a decaying exponential, essentially. So it means that the forcing in time has some kind of correlation scale associated with it, which is just set by this T naught here. Right? So this just looks like a decaying exponential if you don't have this. So you get some kind of finite correlation time, right? So that is your force, and then you smooth the function smoothly varies in time with an exponential decay. Now this is where a lot of the magic happens here. So this is the stochastic term of the differential equation. This is essentially just something that we put it in by hand in k-space. So this is the shape of our forcing function. And then this is a projection tensor that allows us to do either completely divergence-free forcing or completely curl-free forcing. So we can just force on the large scales with vorticity modes, like a washing machine, or we can force on the large scales with compressive modes, like a weird washing machine that does this. I don't know. That is an interesting idea for a washing machine. So, these kind of modes, the modes that in or out, that's your curl zero modes, and the curly modes, the divergence-free modes. So that F naught function just kind of looks like this. It's just a mask in k-space. So we just draw a parabola in k-space like this, essentially. I'm just forcing on the larger scales. And we want to do that because, we have all these scales in that 10,000 cube simulation, and we don't want to touch them. We just want to interact with the larger scales, and we want the higher K modes to do their own thing. So, you get a kind of self-consistent cascade like this. So you set the outer scale dynamical time scale from the forcing as well. And you just essentially keep driving until you get into a state where the energy in is equal to the energy out. And then all the statistics of your simulation become stationary, just flat in time, and you can average over those time relatives. I hope this makes sense. Did that make sense, Dick? I'm going to say that's yes.
Yeah, no, it makes total sense. But you could have other directions by stochastic forcing. So you could actually push some things up scales as well as down scales.
Well, yeah, you can, and you can do that by changing the helicity of the forcing. So this is non-helical forcing. So the curl modes are left-handed and right-handed. But if you make them all left-handed, the energy cascade actually flips and goes to larger scales.
Yeah.
So you can play fun games like that, that's for sure. So this is a very simple model. I want to just put it out there. No gravity, no stars, triply periodic, outflows equal to inflows, in other words. Driven in Fourier space, so we don't have self-consistent driving here by supernova, et cetera, et cetera. And of course, this is also isothermal if you looked at the equation state before. So we're kind of assuming infinitely fast cooling times. And this is probably reasonable for the cold ISM, but still caveats to our modeling. Now let's just look at some pretty pictures. This is the gas density structure. You saw it in my opening slide. You get like kind of 5 orders of magnitude in gas. So this is a big rarefaction in the turbulence. This is a overdense filament. Beautiful kind of fractal structures. You can't see this too well, but this is a map of the current structure. And this is me zooming into the maximum kind of K equals 100 mode or so, which is where we actually do find plasmoids. So we find these plasmoid chains appearing in the current sheets. And you can see this is actually a very small region in the turbulence. And not only that, but it's in a void. So it's in this big current void. And essentially we zoom in, zoom in, zoom in. We do get these nice plasmoids. But they are very, very low volume filling structures in our simulations. So already you might think that maybe these plasmoids that I was talking about before, this asymptotic regime of turbulence, isn't actually realized in the simulations. Magnetic field structures are amazing. I just wanted to show this because I know that there are people who do magnetic polarization in the audience. And I mean, I think this could be the highest resolution polarization map for iso turbulence that ever exists. And I have the MPI tools already built to compute all the Stokes parameters and stuff. So let me know if you're interested. Now I said this is driven turbulence. So this is what driven turbulence really means.
Sorry to bug you. Were those magnetic structures made with the same techniques as the thing that you showed in the prior plot?
Fundamentally, but these are now sliced instead of the full 3D. So this is a slice. You're seeing the gas density in the background, and you're seeing just me integrating through the magnetic field and drawing lines as I go.
And the things that are kind of thick and white, is
That
that
means-
just a huge concentration of B field?
Yeah, exactly. It's just
Oh.
it means that the field isn't. It's kind of like almost a stationary point in the field. What do you call them? You don't call them attractors. You call them limit cycles, I think. It's almost a limit cycle.
Yeah, that's what it looks like.
Yeah. Exactly. So you're drawing lots and lots of lines on top of themselves. Oops, we're gonna have to go through this again, but it actually looks really bad here, but it's nice and smooth on my computer. So many amazing structures in this magnetic field.
Wow.
Okay. Oh my God. I haven't even talked about the results. So, this is what driven turbulence looks like. You start at t equals 0. You drive it with that forcing function until it becomes statistically stationary in time. So we want to get it into this time stationary state so we can essentially grab realizations all across time and then average over them to build the best, most robust statistics possible that are not sensitive to things like intermittency. You don't want to be caught up in one of these big fluctuations. So this is the turbulent Mach number. You can see it is around Mach 4 on the larger scales. This is the alphanic Mach number now. So this is associated with the magnetism. You can see it's 1 over the square root of the energy densities. It's equal to I always think that 1 over the square root of the magnetic energy density. So as the alphanic Mach number goes up, means that the magnetic energy is going down, or vice versa. So down here you're very magnetized, here you're in energy equipartition, up here you're about 4 times energy equipartition or whatever. So you can kind of see that our simulation gets into the stationary state for the magnetic field really, really quickly, which is fantastic. That's what we want. We don't want to waste any time integrating these simulations. And why is that? Well, we actually set up our initial conditions for the magnetic field based on small-scale dynamo theory. And this is what I was talking about last week when we talked about kinematic dynamos and and very early stage dynamos. Essentially, you go through this exponential growing phase into a saturation. So we grab the saturated state from a small scale dynamo experiment. Kind of looks like this. We grab the whole, this is the magnetic energy spectrum divided by the genetic energy. So we grab the saturated spectrum and we put it into our initial conditions for the 2000 cube simulation so that it doesn't waste any time growing magnetic fields. It's just immediately saturated. So now let's talk about some results in the last 15 minutes. Well, there are two very important scales in this whole system. So it's weird to talk about turbulence and scales because turbulence is typically thought of as being scale-free, but this is definitely not the case for supersonic turbulence. You have the first scale, the magnetosonic scale. So this is the scale where, again, the transition between supersonic and subsonic motions. This is the first time this has actually been measured. So we have this first transition scale, and then we have another transition scale, which is the energy equipartition scale, or previously also known as the Alfvénic scale. And again, you have kind of this dichotomy in the turbulence. You have on large scales that it is fundamentally hydrodynamical. These correspond to the scales that are also supersonic. You can't beat supersonic motions with a magnetic field, in other words. Really hydrodynamical here. You know, Alfvénic Mach numbers of 10 larger, or 10 and a bit smaller. And then we have the magnetized set of scales. So this is where the turbulence becomes sub-Alfvénic, actually. So you get into this magnetically dominated state on small scales until you get to the highest K modes that you resolve, where you're about energy equipartition also. And then, of course, you have the transition between these two, the energy equipartition K mode. Now, what does the electrokinetic spectrum look like? Well, I was just showing you these very toy models to begin with, our kind of Kolmogorov -5/3 spectra. This spectrum looks nothing like that at all. I'm showing here a run at 2,000 cubes, 5,000 cubes, 10,000 cubes, all average in time on the same time realizations. And you can see on the large scales, I mean, you get the K to the -2 spectrum. So this is the spectrum of discontinuities. And then as you go to the higher K modes, you get a K to the -3/2 spectrum. So K to the -5/3 never shows its face at all. Again, I think we understand already the large scale spectrum. So let's go to small scales. If you're a keen follower of MHD turbulence theory, this looks exactly like an IK type spectrum. If you're not, I'm going to talk about what that's all about. And essentially what you have to do is somehow reduce the nonlinear interactions in your turbulence to get this. The strongly nonlinear spectrum is uniquely that -5/3. So that's when that, you know, you can kind of think about it as that Reynolds stress term is acting as strongly as possible. We're going to get -5/3 uniquely, but as you go to kind of weaker interactions, you actually shallow the spectrum, and here you're getting -3/2. So there's some shallowing going on. So there's some weakening of nonlinearities in the turbulence. Now, MHD turbulence, we kind of talked about hydrodynamical turbulence to begin with. What's MHD turbulence all about? Well, before this actually goes, what you're seeing here is an Alfvénic perturbation on this side of the domain, Alfvénic perturbation on this side of the domain, and I'm going to propagate those into each other. Okay, so these are, you know, you have your magnetic field line, you have a perpendicular component to the magnetic field line, which is the oscillation in the magnetic field, and then you have a direction for the wave, which is along the magnetic field, and this is an Alfvén wave. And what you're seeing here are contours of the current density. So I'm going to collide. I mean, you can already, you know, there's a time scale associated with this already. It's just associated with with VA, with L, the domain, over VA, the speed of the Alfvén wave. And that will give you the linear time of waves to essentially travel along the domain. But there's going to be another time scale as well. You can see when these waves come in, something happens, there's some deformation. Now they're going out again. And I think that they're going to interact again on this boundary. Unfortunately, it would be nice if Greg made this so they reflect and come back, but they're going to interact over here again. And what you're seeing is more and more structure being generated in these through these Alfvén wave interactions, and that structure is itself a cascade in this case. So that is the generation of more and more fine scale structure every time these counterpropagating Alfvén waves interact. And there's a time scale for that generation of the structure, and that time scale is the nonlinear time scale, or MHD turbulence. So there's two time scales. There's the linear time scale associated with just propagating, and then there's the nonlinear time scale associated with creating that new structure. So a bit different than the regular hydrodynamical cascade. But I just wanted to emphasize that there are these two time scales. Now, we're just thinking about those waves. So as I said, delta B and delta B are perpendicular for alpha waves, but essentially this ends up, when you work out what that perpendicular spectrum is, that spectrum of the cascade forming perpendicular to the magnetic field, you get k to the minus 5/3. So this is, back to your Kolmogorov idea. But if you through some kind of shearing event, or if you just change the alignment between delta B and delta B, so essentially that whole sheet that we've seen, that current sheet is kind of sheared like this, and that weakens the cascade and gives you this -3/2 spectrum. So wow, this looks interesting. -3/2 is prediction back from 2006. Maybe that's what's happening in our turbulence. And you can see down here, this is the nonlinear time scale that I'm talking about. It's just associated with the angle between the counter-propagating alpha waves as they come at you, come at each other and interact. So you can you can essentially slow down the nonlinear time scale by aligning them. You can align the waves, and this will slow down the nonlinear time scale, which will then, of course, create a shallow spectrum. So this is interesting. We go into our turbulence and we compute the alignment. So this is the V and B alignment, okay? And here yellow is, completely parallel, and blue is completely anti-parallel. And, if this was Goldrick and Schradal-like, this should be a black plot. So black is exactly the perpendicular case, but this is just beautifully lit up in blue and yellow and organized very into like these big patches of highly aligned structures in the turbulence. This is very interesting. These are exactly what we want to see, because something is weakening the nonlinearities, and it looks like it's happening everywhere in the turbulence. So of course we can be a bit more quantitative here. We can compute the PDS, but I mean we know what we'd expect. So one way that is not the cascade to test this theory is to test the alignment angle between that V and B vector as a function of length scale. So Boldarov predicts that alignment should be it should be on small scales, it should be very aligned. On large scales, it should be more unaligned. More unaligned, yeah, that's the word. So that's what we want to test. We want to test that if the angle structure function goes like L to the 1/4 here. And this is how you compute that structure function. I don't want to get into details, but we're working in the system of the local magnetic field because that's what we need to do here. You can define, of course, the local magnetic field on any scale that you want, a local mean magnetic field, and you can work in the coordinate system of that mean magnetic field. What we find is not the Boldarov picture. We do find that on small scales we have much stronger alignment, and on large scales we have much weaker alignment. But we find this L to the 1/8 Dow law, and not L to the 1/4. So this is kind of a beautiful problem for theorists now, because there's just a square root factor between the theories, the theory and the simulation. So I haven't actually dove into building a theory for this, but it's ripe, it's ready. So we find scale-dependent alignment, but it's not the standard dynamical alignment picture. Another aspect of this whole problem is that V and B, or in this case I've switched notation, very sorry, U and B, are not the only aligned variables here. So we find that there are many other field variables, B and the current density, so this is the current density, the curl of B, or the velocity, again, the gas velocity, and the curl, the vorticity, also find themselves in highly aligned configurations. All of these configurations reduce every nonlinearity in the MHD equations. This one reduces the one in the induction equation, this one in the Lorentz, or in the momentum equation, this is the Lorentz force. This one is reducing the Reynolds stress through the Lamb vector. So on these small scales, or in the subsonic cascade, you can kind of start cancelling terms out because they're just subdominant. And what you end up with is just the hydrodynamical equations with no nonlinear terms left. You're just left with a very, very simple set of equations. Now this is very interesting. This is incredibly interesting. The magnetic field gets strong on small scales and then just wants to turn itself off immediately. So I'm not going to, this is definitely related to the saturation of the dynamo, but let's skip this because why not? So this is some very beautiful data from the NASA mission, MMS. And what they're doing is measuring the alignment between these variable pairs in the magnetosheet. So this is the place, the plasma between the Earth's bow shock and the magnetopause. So all this stuff. They're making a similar measurement to us, and they find that they also get all this beautiful alignment between V and B, V and omega, J and B, J and omega. So this is very interesting. We seem to get similar results as what's happening in the magnetosheet. Now, how do we get there then? How do we get there? Well, there's this idea in plasma theory called relaxation. And relaxation essentially says that you have some invariance. So you have some total invariance in your plasma. So that is things that do not change over time, or rather things that decay slower than the total energy in time. And these are known, this is the total energy, as the magnetic helicity and the cross helicity. And they look like this. This is the magnetic vector potential. This is the magnetic field. And this is our U dot B from before, the essentially sine angle between U and B. So these things decay very slowly compared to the magnetic energy. So fundamentally, they kind of are invariants in ideal MHD theory. And you can essentially work out, if I perturb this equation and treat it just like a functional, trying to minimize it and work out what minimum energy, a minimum magnetic energy state I get if I minimize this equation over space, I find that my U and B are aligned, my B and J are aligned, and my J and B are aligned as well. So this alignment is some fundamental minimum energy state that my plasma gets into on small scales. Now, if we assume that the relaxation time is actually associated with a dynamical time in the simulation, actually the alphanic time here, we can try to compute the relaxation time divided by the turbulent fluctuations as a function of K mode. And so the principal idea is you have a background fluctuating velocity field, turbulent field, that's constantly perturbing the magnetic field out of this relaxed state. But the magnetic field gets strong on small scales. We saw that it goes above equipartition on small scales, and suddenly it's the thing that rules the roost, right? So it wants to get into a relaxed state, and it's going to do that, and it can do it on shorter time scales than the turbulence is able to perturb it out of the relaxed state. So this is the fundamental idea here. I'm calling it competitive relaxation. It's turbulence versus relaxation. On large scales, where we have the shocks, the turbulence is dominating, nothing is able to relax, everything is thrown around by the turbulence. But you get to the smaller scales, so the magnetic field is turning on, it's running the show now, and it wants to relax because that is the minimum energy state, that's what it wants to be in. So this is very pretty plot, I think. Now there's still lots of mysteries, and I'm so glad that, I think I'm almost done with my slides too, so this worked out. So the cascade has completely cellularized, you would call it. So the cascade isn't happening homogeneously in space any longer. You can't think of the cascade like that at all. In these regions, right, the blue and the yellow regions, as we talked about before, there is no cascade. V and B are completely aligned or anti-aligned. You can't have a cascade. The non-linear time scale goes to 0. Or goes to infinity, sorry. So, but you can have cascade between the interfaces between these regions. So the cascade is completely, it's still allowed to happen. You know, it has to be allowed to happen. We still see the cascade happening, the -3/2. So it hasn't completely halted, even though it has stopped in these regions. It has to be just stuck to the surfaces between these interacting regions now. That's interesting. This is something we haven't explored in detail, but the volume and surface area of these regions matter. It's going to tell us how much of the cascade persists versus how much of the energy is just statically relaxed, essentially, just frozen in space. So, to summarize, the supersonic energy cascade looks like this: burgers on low Ks, large scales, relaxation and turbulence on small scales. very different from this. Well, thank you. That's it. Thanks.
Any questions?
Yes.
Why does the system want to reduce nonlinearity? So if it doesn't reduce this alignment vectors, you're gonna have a stronger nonlinearity, so
Exactly.
energy cascade is gonna be faster down the scale.
Exactly.
What's wrong with that?
What is wrong with that? Well, that is not a minimum energy state
You
for
know,
the
the open
system to
systems,
be
the
in.
minimum energy state argument doesn't really work, right?
Why is that?
Open system don't care about energy.
Even for a open system, we have found that these invariants are conserved on all length scales in the cascade.
Right, so system want to reduce nonlinearity.
So the system wants to.
But I'm trying to understand, what if it doesn't, what will happen? Is
Well,
gonna
if
get-
it doesn't, then it's just strongly nonlinear all the way down, and it should be
So
minus
you're
5
gonna
thirds.
get, you end up with the inverse energy?
No, not the inverse, but this should just be minus 5 thirds.
So it's still not reverse. So why does it want to minimize?
Why does it? I mean, every magnetic field wants to do that.
Yeah, okay, I guess that's philosophical,
Yeah.
I don't understand why, I think open systems don't care about energy.
No, I think this system definitely cares about energy. It cares about its ideal invariance on every scale. And one of those ideal invariances is total energy. This is also how cosmological magnetic fields decay into modern magnetic fields. They care about their invariance. So if anything, it's like you get far enough away from the source of the turbulence, and it's now acting like decaying turbulence. And decaying turbulence cares about its invariance. It cares about its total energy. It cares about its magnetic velocity and cross velocity.
Ask, so when you're trying to picture of alignment and anti-alignment in your magnetic fields,
Yes.
is there, should I be thinking about like, does the velocity, I guess, switch signs between the regions, or is it the magnetic field, or is that not a good way of thinking about it?
Oh, that's a good point. It should be the magnetic field. Yeah, the velocity should still be random, and the magnetic field is the one that's now able to orient itself with respect to the velocity. But I haven't made that calculation, so that is an interesting point. But my intuition tells me that you get down to these small scales, and it's the dynamical timescale of the magnetic field that matters now. You have to treat these differently. You can't put them into a single nonlinear time. And now the magnetic field can orient itself into these minimum energy states, and the velocity field doesn't have a say in the matter. It can't respond fast enough. That's what I was showing with the T-turbo over T-relax. It's about the response to the magnetic field versus the velocity field, fundamentally. Yeah. Just interesting. What's to turn itself off as soon as it gets strong?
Any more questions from the room?
Yeah.
If you go back to the slide where you were crossing out all those terms because of like the orientation arguments,
Yep.
why were we able to argue that like the forcing term is?
Oh, because you're deep in the cascade. You don't care about forcing. Also, I mean, if you're in the middle of the cascade, you also don't care about these diffusion operators, really. And you can see when you cancel out the resistive operator as well, you just end up with nothing happening. So the magnetic field really just becomes completely stationary and stuck in these regions. And that does happen in force-free MHD. That's exactly what happens.
It's also no nonlinear terms whatsoever. So who's cascading?
That's exactly what I was saying. The cascade is now stuck on these very thin surfaces between the regions.
Where it's not.
Yeah, where it's not, because this is perpendicular in black. So that's where the cascade is strong. It's really interesting though, right? It's not happening everywhere homogeneously in space. And if your ISM is stuck inside one of these regions, I mean, you shouldn't care about turbulence. Turbulence doesn't happen.
It's random.
There's no cascade. So really the size scale of these regions is also very interesting, just in the context of a galaxy.
do you know how it scales with the various, magnetic Reynolds number, et cetera? That area or that volume?
Well, no. It shouldn't scale with the Reynolds number or magnetic Reynolds. I don't think it could scale with the magnetic Prandtl number. I'm not sure about that, but I don't think, as we go to higher and higher RE and RM, we just resolve more inside the region. I don't think we should change the intrinsic size.
So a counterexample of that is the old experience by Liebscher, where he's looking at, heating a volume and changing the amount of force in there. And he showed that you keep getting different solutions even though you went to Reynolds numbers of 10 to the 20, and it never came.
Is this in 2D or what is this?
No, it's 3D.
Oh.
But it's hard lids.
Yeah.
So there's a boundary, there's a weird boundary condition.
Yes, but that's a boundary condition problem, isn't it? Because isn't that associated with the aspect ratio? Is that what you're talking about? Yeah.
Well, what he did is force the amount of heating.
Yeah.
So you don't ever see.
I don't think this is an aspect ratio problem.
Well, the point is, the intuition is that when you go to some infinite Reynolds number, it doesn't matter anymore. But that's not the case when you have a boundary condition, and it might not be the case in a situation like this.
Well, I mean, this should be happening on small scales regardless of the global boundaries, I think.
I would have said the same thing before seeing that experiment.
Yes.
That experiment.
Yes.
So you've got to be a little careful.
I mean, stratification changes this picture on large scales, but as soon as you get to small scales, stratification should.
So that won't matter.
Yeah.
But I'm just saying that, your intuition normally is that if you got somewhere that goes to infinity, you don't care about it after a while. But infinity could be a lot bigger than you think it is.
Yeah, that's true. That's why we were testing these asymptotic seismoid regimes.
You were saying you got up to 10 to the 8 or whatever. No, what'd you get up to?
10 to 6. 10 to 6.
Yeah, and it goes up. You need to go up to 10 and 20.
Okay.
And there might be
Give me
something
the compute
happening.
time, I'll do it.
Yeah, exactly.
Give me 100,000 cube experiment.
Right.
Cool.
Dick, do you have a question?
Actually, I'm glad you're on this page. I completely agree with Iona's comment in the chat that it's an absolutely beautiful picture, but I still don't understand what it means. So you had a little bit of discussion about the characteristic scale, but you can see that at the bottom left, the scales are a little shorter than in a lot of the other parts of the medium. So, but if you, for example, I mean, this is just the V dot B, but if you did a transform, how would it look? So here's what I'm trying to get at. I'm trying to make the analogy, it's probably wrong, with instabilities where you have, plus minus regimes, domain walls, and all that kind of stuff.
Yep.
And that can breed topological things happening. Is there any possibility that we're looking at some kind of topological structures in the transition going from the yellow to the blue? I mean, you said that the boundary between them is where all of the action is occurring.
That's right, yeah.
And that makes sense to me. But the relative quiescence of the interior regions sort of speak to, these big plus and minus plateaus or something.
Yeah. No, it's a good point. So what you're interested in is if the magnetic helicity maps onto the cross helicity, because the magnetic helicity is capturing the topological changes in the magnetic field. I think that's what is that what you?
I think that's exactly what I'm getting at, but you're putting it into somewhat better words than I would have. But yeah, I mean, it looks to me like there's a lot of exploration still to be done here in order to understand.
Oh, definitely.
Scales of the structures. So this is all pretty new.
Oh, this is brand new. So this is submitted last week to Science. So
you're going to get it. You're going to get a cover with this picture. How could they resist?
Yeah.
Well, because it's not biology, but okay.
Yeah, it's not biology. So that was just rejected.
Well, you could change the fraction, and you could say it's some sort of internal. Anyway, yeah, very beautiful.
Yeah, there's still lots to do. I agree with you, Dick. All right. Oops.
Right, let's thank our speaker again. snacks upstairs. You can keep asking James questions over snacks.
So that picture with the black stuff. Did you made a movie of it? Did it go static or is it bouncing around a bit?